Okay, let's do an example that incorporates both bending stress and shear stress into a design problem. Okay, let's take a beam. Our x-axis, y-axis, and we're going to apply a constant uniform load. W. We have length equal to 28 feet, which is 336 inches. And the cross section of this is a plywood web. And then we're applying 4 end caps. Each of these end caps is 3.5 by 3.5 inches. And this is a thin sheet of plywood. And the height is 20 inches. I said this is a design problem, so we don't know the thickness of that plywood. We're going to solve for the thickness. But what we do know is that we have some allowable values. Our allowable stress in the end caps is 4,000 psi. And our allowable shear stress in the plywood is 1,600 psi. So I'll draw some connecting arrows. So the allowable shear stress has to do with the end caps. Sorry, allowable normal stress has to do with the end caps. Allowable shear stress has to do with the plywood. And our objective is to select the plywood thickness. Okay, very first step is we need to get our shear and moment diagrams. Right, whether we're calculating bending stress or shear stress, in either case, we need to know either V or M. Okay, what does our shear diagram look like?
Up as a reaction, and then it's going to be a slope. Well, we don't have to jump. Anyway, it's going to go downwards, then go up.
Perfect. What are the magnitudes of these maximum values? Okay, WL/2 or W times 336/2. One's positive, one's negative. And of course, this slope is negative W. What does this moment diagram look like? Parabolic is going to go up or down? Up, and then I guess back down. Okay, and what's this maximum value of moment?
That's going to be the area of that triangle.
Yep, the area of this triangle, which is?
WL/2 times L/2.
Okay, so WL/2 times 1/2 times L/2. So that ends up being WL²/8. All right, so where on this beam do you expect to have the maximum bending stress, maximum normal stress? At the middle, so I think you mean right here, somewhere along this line. Okay, now within that cross section, where will it occur? So the top or possibly the bottom, depending on whether we're talking tension or compression. Good. What about maximum shear stress? I'm sorry, I didn't hear that. Okay, so when you say middle, do you mean this middle or this middle? This one.
What was the second one?
That second one. Okay, so it's somewhere on that centroidal axis. And where along the length? At L over 2? I'm not quite sure where you're, oh, I see. Okay, you're saying the height over 2? Yes, we've established that. So that's this line. Yes, it's on this line, but where on this line?
So on the side.
Okay, so on the far left and the far right, because that's where the shear diagram gives the largest V.
Yeah, that's
Right, so the equation is VQ over IT. We have a T is changing actually, so that may throw a wrench in it, but oh no, I take it back. For the sheathing, for the plywood, it always has a constant. Yeah, but that's not important. Okay, so disregard, I mean, T is changing, but let's not worry about that. V and Q, V is largest on the ends, Q is largest in the middle of the cross section. So that's where we're going to have this largest. T does get bigger on the ends, but that only decreases our shear stress. So that doesn't help us to find our maximum value. The maximum will likely be where all three of those coincide. You have your highest V, your highest Q, and your thinnest B. They're the same, and I use them interchangeably. It just depends. It depends what textbook you're looking at and what context, but they're the same.
But that's going to be the thickness of the plywood?
Yes. Yes. Because we're looking specifically at that height, and so therefore it will be that thickness. Yeah.
So in that equation, it's VQ divided by moment of inertia times.
Yes. All right, so the two equations we're using are bending stress is negative my over I. So it's moment times vertical distance divided by moment of inertia. Shear stress is negative VQ over IT. And that's exactly what he just said. It's the shear force times Q, which is that first moment of area, divided by moment of inertia and divided by width. Now I do want to clarify, if you look in the textbook, you may see that they don't include this negative sign on negative VQ over IT. I contend that it's important, and I think the reason it's important is because it tells you what direction the shear is going, whether it's going up or down. That may not be important in the case of a simple beam, but when you get into a situation where you're trying to superimpose loads, say you have a beam that also has torsion, now it's really important which direction that shear is going. Because the shear, we'll talk about it when we get into shear flow, but they're going in different directions. You're gonna need to superimpose them, and you need to know this direction. So numerically, it's fine if you leave that negative sign off. The only thing it's doing is telling you which direction this flow is going. Okay. And if you ever forget, you can always go back to how we derived the shear stress. if you know your bending stress on one side, bending stress on the other side with two different X values, the direction of the shear flow has to put that into equilibrium. So you can always go back to that little picture and figure out which direction your shear stress is going. Okay, so these are our equations. And we know the centroid is on a plane of symmetry, and so y bar is 10. We can do that without any math. We can just observe that this is symmetrical, and therefore our centroidal distance is 10. We need to calculate I. I is going to be the sum of 5 different I values. So each of those end caps has an I value associated with it. And fortunately for us, those are all identical numerical values. So we can say that I equals 4 times the I of the end caps plus the I of the plywood. Maybe I'll make that. PL is fine. Oops. So the end cap is 1/12 BH cubed plus D squared times area. So 1/12 times 3.5 to the 4th plus, now this is gonna be 10 inches minus half of the 3.5 inch height for the end cap. That would be the distance between the centroid of the overall shape and the centroid of an end cap. And that, of course, gets multiplied by 3.5 squared. And that is equal to 846 inches to the 4th. Now the the plywood is 1/12 times the thickness, which we don't know, so we'll call that T, and the height cubed. Well, the height, though, we can plug in 20 inches cubed, so we get 667 times the thickness. Therefore, I is 667 T plus 846. Yes, question?
So you're defining the origin at the bottom of that shape, since your y bar is 10?
No. So this is my centroid. I'm saying that this distance here is 10. Okay, so if we want sigma max, let's start this on a new slide. You got everything you want? If we want to calculate sigma max, we're going to use x equals L over 2. And we're going to use y equals half of the height. So sigma max is at x equals L over 2. And y equals negative d over 2. I'm saying negative because I'm going for the tension. And we're assuming this is under positive bending. Okay, so sigma max, I guess that's not an assumption, that's the case. So m, we said, is negative w L squared over 8 times negative d over 2 over I. So let's plug in. W in this case is a negative value, so that negates that. And L needs to be 336 over 2 divided by 8. Do you think it wouldn't? You're questioning
Yeah.
the over 2?
336.
We already calculated the
Oh, in the 8.
in the 8.
Perfect. Thank you. So you're right. You're right. We use the total length there. That's not an X, that's an L. Sorry about that. Okay, WL squared over 8. So W 336 squared over 8 times negative 10 divided by 667T. And then the rest of this, oh, you know what? Let's go back. Is it okay if we go back? This is wrong. This has to be times 4. Right, there's 4 of those end caps. Okay, so this is plus, it ends up being 3385. That's 4 times that 846. And I know that this cannot exceed 4,000 PSI. So now what I have is I have an equation of the loading W and the thickness T. And that equation ends up being W equals 95.95 plus 18.9 T. So the amount of loading that I put on it increases as the thickness of that member increases. Cool, we're going to set that aside for now. We know that this is the equation that causes failure in the end cap. So it's the loading that causes failure in end cap. But now we want to go back and we want to look at the plywood, because there could also be failure in the plywood. And we know that that sheathing is negative VQ over IT. We know that 1600 PSI is the value at which it's going to fail. And V, the maximum V is negative WL over 2. So it's negative W times 336 inches over 2 multiplied by Q. Did we calculate Q yet? No, we did not calculate Q. Okay, we will do that here. So we have 2 end caps. The centroid of those end caps is 10 minus 3.5 over 2. So that'll be our Y bar. And then the area of each of them is 3.5 squared. But now we also have half of the plywood. So we have Y bar, which is 5, right? The total height of half of the plywood is 10. So Y bar is only 5. And then we're going to multiply by the area. The area is that height of 10 multiplied by the thickness. So that gives us Q. I, we already know, is 667T plus 3385. And then the thickness is T, the thing we're solving for. So this gives us the equation that W equals 3.42 times 10 to the 6T plus 1.07 times 10 to the 6 t squared all over 202.13 plus 50t times 2 over 336. So this now gives us the loading that causes failure in the plywood. So if we knew our loading, we could solve for the thickness. If we knew the loading, we could solve for the thickness that was required to cause failure in either one. But a more interesting question is, what thickness of plywood can we put in there so that the capacity of the end caps is perfectly matched with the capacity of the plywood? So we'd expect the failure to happen at the same loading.
So W should be would be the same.
Right, we want W to be the same for both equation, and that will give us failure at the same time, or at the same loading. And so we set these two equations equal to each other, and now we just have the one variable t, and we solve for t equals 0.707 inches. But here's my question to you. Is this your answer? Do you use 0.707 thick plywood? All right, you're gonna round up to 3/4 inch. I guess round up or round down, depending on whether you want to have, these failures are gonna occur close together, but depending on whether you want to be sure it fails in the end cap versus the sheathing, you would pick one versus the other, right? Or if you don't really care which it fails in, but you just want it to be similarly strength so that you're not providing excessive capacity, which means excessive money in either location, then you would round to this nearest, which is 3/4. So you're gonna say use 3/4 inch plywood, and then my end caps will be roughly the same capacity as my plywood. And last thing I just wanna state is that in general, our shear stress is not going to govern. Typically, our shear stress is gonna be significantly smaller than our bending stress, our normal stress. There are a few cases in which the shear stress is significant. One of them is I-shaped beams or thin-walled sections, which is what we're going to talk about next time we meet. So when you have shapes like an I-beam that consist of thin sections, now the shear ends up contributing more to the failure, or more likely to cause failure than for, say, rectangular shapes. Shear also becomes a large impact on the design when you have short beams. That means your H/L ratio increases, so the height of your cross-section relative to your length increases, and then shear becomes larger compared to the bending stress. Also in connections, so we're going to talk about shear flow next time as well. If you have two members that are connected with, say, welds or bolts or even nails, this force has to get transferred through those, and even though maybe it's not going to lead to the failure of the member itself, say the piece of wood, it might lead to the failure of what's connecting it to another piece. And so it's very important that you quantify the shear stress to get the amount of shear force that you're transferring through a connection. Any questions? All right, thank you very much.